So welcome you all in my next lecture. So in my last lecture I talked about the existence of total derivative, directional derivative, partial derivative, relation between directional derivative and the gradient vector. Of course I introduced the notion of gradient vector and some necessary conditions. So now in this lecture I will talk about some sufficient conditions of differentiability, and then we will have chain rule and then tangent plane and normal line. So that's my plan to discuss about those concepts in I think this lecture or maybe next lecture. Okay. In my last lecture I already said, okay, the necessary conditions for existence of total differentiability of x naught or if total derivative exists. Now as I promised, that means is there any sufficient condition, that means existence of partial derivative should implies the existence of total derivative. Answer is yes. So this is I have written as a sufficient conditions for differentiability. Like let f is a map from Rn to R, where S is an open set in Rn. Take a point x naught in S. Now if all the first order partial derivative of f exist and continuous in a neighborhood of x naught, that is very important, then only I can talk about that my function f is differentiable. That means the earlier examples I have calculated, there I say that okay, look, that partial derivative exists but my function is not differentiable. That means if you calculate the partial derivative, that means suppose I am talking about the existence of differentiability at some point x naught, you just calculate the partial derivative in a neighborhood of that point x naught and you can check that partial derivative is not continuous. Because if it is continuous, then this theorem tells you that it has to be differentiable, but the function is not differentiable. So that means I need some more conditions on the partial derivative. That means just not the existence of partial derivative at a point will tell you the existence of total derivative. Not only the existence of partial derivative in a neighborhood of that point also tell you the existence of total derivative, but I need the existence of my first order partial derivatives in a neighborhood of that point, along with it should be continuous. That is very important, the continuous in a neighborhood. So not only existence in a neighborhood will not tell you, it has to be continuous at the point x naught. Then I will say that yes, my function is differentiable. So I am not going to prove the theorem, but this is a very nice theorem. That means this is sufficient conditions. So like if I want to talk about the existence of differentiability of some point x naught, instead of going through the principal definitions to check the differentiability, this is another way to check, like calculate the partial derivatives in a neighborhood of that point and check whether this partial derivative are continuous or not. If you somehow prove that yes, this partial derivative are continuous at that point, then by this theorem you can say that yes, my function is differentiable and total derivative exists. So for example, one very simple example I have given, this is a function f of xy. So this is of course clearly it's a, but we can check it's a total derivative exists. But how to prove that my function is differentiable? I use that theorem. So you just calculate the partial derivative, that means del f del x at the point xy, which is you can easily calculate 2x, del f del y at the point xy you can easily calculate, that is 2y, and this is a polynomial functions 2x 2y, these are continuous functions, and hence by my earlier theorem it is my function is differentiable. Another example I have considered, f from Rn to R, norm of x square. What is norm of x square? So this is x1 square, x2 square up to xn square, right? If my x is x1, x2, xn, again this is a kind of extension of actually this one, x square plus y square. Now I am in n variable. Again you check all the partial derivative exist, and what about the del f del xi at the point x1, x2, xn? It is nothing but 2xi. Okay, so and therefore they are continuous, so therefore my function is differentiable. Again this, look at the function g. Again this is a very nice function, it's a combination of exponential and cosine sine functions. So you can also check that partial derivative, if I calculate del g del x and del g del y, again it will be a combination of exponential function and trigonometric functions. So therefore these are continuous functions, and therefore by sufficient conditions for differentiability that partial derivative exist and they are continuous, so therefore my function is differentiable. In other words, total derivative exists. So this is some properties, like in the case of real valued functions with real variable, that means sum of two differentiable function is differentiable, scalar multiple of a differentiable function is differentiable, and then composition function, that means chain rule whether this is true or not. Answer is everything is true in this setting as well. Okay, so let f is a function from a subset of Rn to R, g is a function from some subset a subset of Rn to R, S is an open set, x naught is a point in S. If f and g are differentiable, differentiable means that is total derivative exists, then the sum is also differentiable. Not only that, the derivative of the sum is nothing but the derivative of f times plus derivative of g. Scalar multiple, that is also differentiable. Derivative of lambda f is nothing but lambda times lambda will come out, if derivative of f at x naught. Composition, if it makes sense, then we will have the chain rule. That means if h is a function from R to R, if it is differentiable at the point f of x naught, and h composed f, if makes sense, then I want to talk about composition functions, because composition function is a map from where to R. Again, it's a map from Rn to R. So therefore, I can talk about the existence of differentiability of the composition function h naught f, or existence of total derivative of h composed f at the point. And this, as I said, say h composed f is also differentiable. Not only that, the total derivative of the composition function is nothing but the derivative of h at the point f of x naught, because it is, I assume that h is differentiable at the point f of x naught, times the total derivative of f at the point x naught. So that means whatever like the usual way it is true, the like similar sort of observation are true in this setting as well. So just by using chain rule, you will have some formula that might be useful to calculate some of the exercise or some problems. So that's I have just noted down. So let x is a function from some open interval a b to r, y is a function from open interval a b to r, say two real valued functions on open interval a b. Then I am considering a set D which is a subset of R2, where u is running over the range of x and v is running over the range of y, and suppose it is contained in the set S. Okay. Now if let z be a functions from the set D subset of R2 to R, okay, defined by z is equal to z of x comma y, where x y running over D. Now if the function x and y are differentiable, then the function z is also differentiable in D. And not only that, I can talk about the derivative of z with respect to t, because since xt and yt are differentiable, so this function t goes to z of xt comma yt, right. This is the functions. Okay. So it is a function from where to where? It is a function from t running over what? Open interval a b, right. And what is the range of z? This is also r. So it is a functions from R to R. Okay. It is a functions from R to R. So I can talk about the derivative of z with respect to t variable. So it says that suppose x t y t are differentiable, z is differentiable on D, because z is a map from R2 to R, then this function t goes to z of x t y t, that is also differentiable, and derivative you can write in terms of the partial derivative of z and the derivative of x. So it says that del z del x times dx dt plus del z del y times, okay, I think this should be dy dt, there is a typo, dy dt. So I think I should write this is del z del y then dy dt. Some example, suppose this is my function zxy is equal to x square y, x function is t square, y function is tq, just calculate dz dt. So this is the formula. This dz dt is nothing but you just calculate the partial derivative of z with respect to x variable and take the derivative of x with respect to t, and you just add it up. This is very easily you can calculate and you will have this answer. So this is one of the uses of chain rule. Using chain rule you can have this observation. Yes. Another way, so the earlier one what? Earlier one x is a map from R to R. Now this time I am taking x is a map from R2 to R. That means x is a function of u and b, y is a function of u and b. So once it is a function of two variables, so that means I can talk about the existence of partial derivatives. So two variables are there. So the multivariables are there. So I have first, suppose x and y have first order partial derivatives at the point u comma b, and if z is equal to fxy, which is differentiable at the point x u b and y u b, then this function has first order partial derivatives at u b, and then you will have the formula del z del u and del z del b, because in this case what will happen, you have a map from u comma v to f of I think z, which is nothing but f of x of u b comma y of u comma b. So it's a map from R2 to f is a map from where to where? It should be a map from f z of f x y, right. So that means it should be z is equal to f. So f z is, and if z is f x y, so that means, so this should be r. So that means I can talk about the partial derivative. That means it's a function from R2 to R, like, so that means del z del u del z del b, right. And what is the formula, or how to calculate del z with respect to u variable, del z with respect to v variable. So, this is you just calculate del z del x and then del x del u plus del z del y del u, del z del v is nothing but del z del x del v, del z del y del v. Same thing. In the earlier example, we will have a functions from R to R. This time we will have a functions from R to. So, like x is a function from x of u v, y is a function from y of u v. So, that is the partial derivatives are coming into the picture, and this is the corresponding formula. One example I have given. So, take z of x y is e to the power x y, x of u v is 2u plus v, y of u v is u by v. Then you calculate del z del u and del z del v. Okay. So, I think this is a typo. This is typo. So, del z del u, you use that formula, you will have this one. That means you just calculate the partial derivative of z with respect to x, and then partial derivative of x with respect to u and v, partial derivative of z with respect to x and y, and use this formula. That is it. And this exercise also you should try. Okay. So, here also instead of u v, I will have a polar form like r and theta. So, then I say that, okay, calculate del u del x, del u del y, del 2u del x 2. So, that means del u del x, you just make del u del r del x, and del u del theta del y, something like that. So, that means you make this uses of this above chain rule, try to put it like x is a function of r theta, y is a function of r theta, given function z, you write in terms of r and theta and use that formula, then you will be able to do that. This is applications of chain rule or uses of chain rule, this is the formula, you can do that. So, this like I have a functions, if I have a functions from Rn to R or some open subset S of Rn to R, then I talked about like partial derivatives, then I talked about directional derivative, then I talked about the total derivative or differentiability of f. There are many connections and some examples which says that existence of partial derivative and directional derivative will not imply the existence of differentiability. Necessary condition I have discussed, sufficient condition I have discussed. So, that means now the part is remaining. There mean two case of functions I already discussed. One is that vector valued functions of real variable. So, that is like similar extension of the real valued functions of real variable. Appropriate extension is very kind of straightforward extension is there. However, if I have a scalar field, that means real valued functions of several variable, there it is not that easy. That is why the notion of partial derivative, directional derivative, total derivatives comes into the picture. Now, I will have the case 3. Case 3 means suppose I have a functions from Rn to Rm. That means the right hand side is multivariable, left hand side is also multivariable. So, in that case what will happen? If you kind of remember that when I was talking about the existence of differentiability of a functions f from Rn to R, if you remember I talked about the linear transformation and then they either say that, okay, so derivative is nothing but a linear transformation and that some quotient norm is goes to 0, and then I say that, okay, since I am having a functions from Rn to R, so the numerator norm is equivalent to mod. That time I already said you just replace that modulus by the norm, because in the range case earlier it was in R, so that means mod was playing a role. But this time now if I have a function from Rn to Rm, same definition will be there, except you have to just replace the mod by norm, because you are playing with Rm, no more R. So, m is greater than 1. So, therefore, the same definition will be true. That means, if I have a functions f from Rn to Rm, if I want to talk about the existence of differentiability at that point, you have to have a linear transformation from Rn to Rn, and you have to see whether the limit of h goes to 0, norm of f of x naught plus h minus f of x naught minus that linear transformation acting on h, and numerator should be, you have to calculate the norm in Rm, because the value of f is taking in Rm, denominator is actually I am in Rn, because it is the domain of f, the Rn norm, and see whether this limit is 0 or not. If this is the case, then I say that yes, my function is differentiable or total derivative exists, and which is nothing but that linear transformation. So, same definitions I will have in the setting of Rn to Rm. And later you will see, like, okay, let me just talk about that. Okay. So, like this is the I should say case 3. So, this is actually the more general one. So, that means if I have a function from Rn to Rm, then what will be the notions of differentiability in that case? It is like the similar sort of things like whatever we have already discussed from Rn to R. So, take U subset of Rn open set, f is a map from Rn to Rm is differentiable at the point x naught if there exists a linear transformation Rn to Rm such that this limit it goes to 0. What is that limit? Norm of f of x naught plus h minus f of x naught minus the linear transformation acting on h divided by norm h is 0. If this is the case, then I will say that the linear map L is called the derivative of f at x naught, and this either notation df at x naught or df of x naught is nothing but the linear transformation. Again I already said, so in the Rn to R case, f is a map from Rn to R, that this is the another notation f prime x naught or df dx. So this is not so useful, but this is the one useful notations, or this is the one useful notations. Okay, so if I have a function from Rn to Rm, like you know the differentiability of a function from R to R, this extension is not so straightforward. That means in the case of differentiability of a function f from R to R, you have to see the definitions or the definitions of the differentiability of f in a different way. That means in terms of the linear transformation, somehow you have to see the object, and then appropriately you have to extend in the case of Rn to Rm. So that is not so straightforward. So in that case, that means derivative is a linear transformation, not at all a number. Okay, so that's why you have to see, and then the appropriate object will be there. So now, but here since you can ask this sort of questions, so I am functions f from Rn to Rm, then you say that okay sir, so suppose you have a functions f from Rn to Rm, then I know the coordinate functions because I have a functions f like say from Rn to Rm. Then in the beginning of my lecture I said that this f will have a representation like component functions f1, f2 up to fm, right? And what is my fi function? Fi functions is a map from Rn to R, 1 lesser equal to I lesser equal to m, right? So if I have a function f from Rn to Rm, then I will have m component function. Each of the functions are into R, and I already talked about the existence of total derivative of those kind of functions. That means real valued functions of vector variable. Okay, that means scalar field. So now you can ask this sort of questions whether the existence of total derivative of f Rn to Rm has any connections with the existence of total derivative of component functions. This is natural, like when I talked about existence of limit, continuity, some kind of relations are there. What can I happen here? Answer is yes, you will have a relations with the existence of the total derivative of f from Rn to Rm with the existence of total derivative of the component functions, which are real valued functions of vector variable. I think in the list, yes, so that's the kind of theorem I have said. This is the characterizations of differentiability. It says that consider a functions f from Rn to Rm. This is the corresponding, as I said, this is the component functions. You can always write a functions f from Rn to Rn as a component function f1, f2, fm, where each fi is a functions from Rn to R. Now look, f is differentiable at x naught. Just now I have discussed, that means the limit h approaches to 0, numerator is Rm norm, denominator is Rn norm. Numerator is f of x naught plus h minus f of x naught minus the linear transformation acting on h, that Rm norm divided by norm h Rn norm, that should goes to 0. If this is the case, then each component function fi is differentiable, that I already discussed for real valued functions with vector variable, and vice versa. That means if all the component functions total derivative exists at the point, then my function is differentiable. Not only that, since in this case if I have a function f from Rn to Rm, if the total derivative exists, then it will be a linear transformation from where to where? It will be a linear transformation, that means df at x naught, it will be a linear transformation from where to where? Rn to Rm, right? Then it will have a matrix representation. And what will be the matrix representation? So this is okay, I will talk about that. Before that, so this is the linear transformation, that means total derivative of f at x naught, and what will be the action on, since it is a linear transformation, that means if it acts on a vector h in Rn, it should give a vector in Rm. And what is that? It is very nice. It says that what you do, since my function is differentiable, so each of the component function is differentiable. Since each of the component function is differentiable, that means the component functions all first order partial derivative exists. That means I will have the existence of gradient vector, that means del f1 x naught exists up to del fm x naught exists. What we have to do, you just take the dot product with gradient vector times h, comma dot product of gradient vector of fm with h. So this is the vector which is the actions of the total derivative of x naught at h, and this is a vector in Rm. So that is another formula. Okay. So therefore, so if my function is differentiable, if I somehow know the existence of total derivative of the component functions, then component functions, you know if it is differentiable, that means you calculate the gradient vector, take the inner product with h, make a m component like del f gradient of f1 at x naught dot h dot 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 gradient of fm at x naught dot h. This is nothing but the total derivative of f at x naught acting on the vector h. So, as I said, so since this is a linear transformation from Rn to Rm, so that means it will have a matrix representation. So, what will be the order? It should be an order m cross n, and then you will have exact representation. So, the matrix of df x naught is called the Jacobian matrix of f at x naught and is denoted by j suffix f at x naught. And you can write, so if my function is differentiable from Rn to Rn, you can write the Jacobian matrix of f at x naught in terms of the partial derivatives of its component functions. It actually follows from there. Look. Yes. So, Jacobian matrix of f from Rn to Rm. So, Jacobian matrix of f at the point x naught, if my function is differentiable or total derivative exists, it's an m cross n matrix whose ith j entries is nothing but what you have to do. So, aij, so it should be a m cross n matrix, right. So, it would be a m cross n matrix. So, what will be the ijth element? Ijth element is that you say that, or it says that you take the fi, the component fi. So, you have f1, f2, fm components, consider the fith component, it will be a map from Rn to R. That means, since it is a map from, so fi is a map from where to R? Fi is a map from Rn to R. So, that means I can talk about the partial derivative of fi with respect to x1, x2 up to xn variable, because it is from Rn to Rm. Okay. So, Rn to R. So, therefore, what we have to do, aij, you take the component function I and consider the partial derivative with respect to jth variable. Okay. That stands for a suffix ij. So, if as a suffix ij means consider the ith component function and take the partial derivative with respect to j at the point x naught. So, that is the notations. So, jf at the point x naught, this is nothing but a gradient of f1. So, this is a what? Gradient vector, it is an n component, right. So, that means del f1 del x1. So, that means if I write, what is this? This is nothing but gradient f1 at the point x naught. What is this? This is a n component. So, that means del f1 del x1, okay, at the point x naught, comma del f1 del xn at the point x naught. Okay. And what about this one? This is also n component. So, fm at the point x naught, which is nothing but del f1 or sorry del fm with respect to x1 at x naught dot 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 del fm at the point del xn, because it is a map from Rn to R, right. So, this should be at x naught. So, that means you have n vector and you have m rows. So, that means it's a m cross n matrix with ith j the entries are, you can easily remember aij means first I stands for the ith component of f and j stands for the partial derivative with respect to xj variable, that is it. So, this is del fi del xj at the point x naught. For example, I have given a functions like fxy. So, it is a map from where to where? It is a map from R2 to R3. That means the derivative or Jacobian matrix at the point say AB will be of order what? So, this is R2 to R3, right. So, it should be a 3 cross 2 matrix, right. 3 cross 2 matrix means 3 rows, 2 columns. 3 rows actually are connected with the component of F. So, that means since it is a map from R2 to R3, how many 3 components should be there? F1, F2, F3. So, you put it as a row. So, that means this is, look, F1 is first row, F2 is second row, F3 is third row. So, that means in the rows actually the component of F, okay. And what will happen, the column is nothing but it is from R2 to, R2 means you have 2 variable x and y. So, first we take the F1 with respect to x variable and then y variable, x variable, y variable. So, this is the corresponding Jacobian matrix at AB. So, that means this is del x del f1 at AB, del I del f1. That means you put row in the component vector and the column is that it is a map from R2 to R3, only 2 components or 2 independent variables are there, x1, y. So, we calculate the partial derivative with respect to x and with respect to y. For example, this function again it is a map from where to where? It is a map from R3 to R2. So, what will be the Jacobian matrix order at the point say ABC? So, it should be order 2 cross 3. Then it will have 2 rows, 3 columns. 2 rows means component, take the component functions F1, F2. So, look, this is in the rows, okay. This is in the rows, 2 rows. And what about the column? Column comes from the R3. R3 means it will have 3 variables independent x, y, z. I mean del x, del f1, del I, del f1, del z, del f1. Similarly, in that second row, del x, del f2, del y, del f2, del z, del f2 at the point ABC. So, therefore, if my function is differentiable, I will have the matrix representation of the total derivative, and that is called the Jacobian matrix, and that can be written in terms of the partial derivatives of the component functions. few examples I have given. Okay, if my function f of x y is equal to this, you can easily identify the component functions. So this is my first f1, this is f2, this is f3. So this is f1, this is f2, this is f3. Using the earlier formula, you just calculate the Jacobian. Similarly, it is a function from R3 to R2. So this is f1, this is f2. So what will be the orders? It should be order 2 cross 3 and 2 rows and 3 columns. And here it's a map from R2 to R3. So this is a map from R2 to R3. So that means 3 cross 2 matrix. I mean 3 rows, 2 columns. 3 rows coming from the component functions f1, f2, f3, and the derivative coming from the derivative of respective x variable and y variable, because it is from R2 to R3. Okay, that you can easily calculate. I am not going to do that, but you can easily do that. So then it will have a chain rule will be there. So what is chain rule? Chain rule is that, okay, if I have a functions x from R to Rn, which is a differentiable at the point t naught, and if I have a function say f from Rn to R, which is differentiable at the point x of t naught, which is nothing but capital X suffix naught, then the composition function f compose x is differentiable at the point t naught. Not only that, so what is this function? F composition function. This is t goes to f compose x at t. So it's a map from R to R, right? Okay. So it's a map from R to R. So therefore, I can talk about the derivative of the composition function f of xt at the point t is equal to t naught, and this if my x is differentiable at the point t naught, f is differentiable at the point x naught, which is nothing but x of t naught, then composition function is also differentiable at the point t naught. Not only that, the derivative is nothing but the gradient vector of f at x naught dot product with derivative of x at the point t naught, and which I have written in terms of, we have the write the gradient vector, write the derivative of x prime, and this is nothing but the dot product, and this is the expression I from 1 up to n del f del xi at the point x naught times derivative of xi at the point t naught. Proof is very straightforward. Since f is given to be differentiable at x naught, so therefore what will happen? So if you remember, f is differentiable means what? Limit h approaches to 0, norm of f of x naught plus h minus f of x naught, right, minus derivative of f at the point x naught acting on h, and which is nothing but your gradient vector dot product with h, this norm, right. If you remember, this norm divided by norm h should go to 0, right, that is what it is. So that means what I am saying is that I am just writing the same object divided by norm h. If you divide by norm h, it will be error term. So I am just writing this is limit h goes to 0, e of h actually is 0. Sometimes this is called the error term. Okay, so this is actually 0. So so that means if f is differentiable at the point x naught, so that means f of x naught plus h minus f of x naught minus the derivative of f at x naught acting on h, which is nothing but the gradient vector dot h divided by norm h, that means you will end up with e of h, that should go to 0. Okay, so that is given since my function is differentiable. Here e h goes to 0 as h approaches 0. In other words, this is the things. Okay. Then what you have to do? So you just replace h by this xt minus xt naught, because h is a vector where? H is a vector in Rn, x is a map from R to Rn, so xt is a vector in Rn, xt naught is a vector in Rn, so difference will be a vector in Rn. You consider xt minus xt naught as h, because this is true as h approaches to 0. Now look, if t approaches to t naught, then what will happen? Xt minus xt naught, because x is differentiable at the point t naught. So that means x is, since it is differentiable, it is continuous at the point t naught. So t goes to t naught means norm of xt minus xt naught, that is also goes to 0 as t approaches to t naught, right, because it is continuous at the point t naught. So differentiability implies continuity. So that means norm of h goes to 0. So that means you just replace this one by xt minus xt naught. Use the fact that x is differentiable at the point t naught, that means it is continuous at the point t naught. You will end up with that this my function composition function f of xt is differentiable. Not only that, its derivative is nothing but exactly your gradient vector times x prime of t naught, because what will happen, look here. So here if I replace h by xt naught, so what is x naught plus h? So h is equal to what? Xt minus xt naught, right? But xt naught is what? Xt naught is nothing but x naught is there, right? So therefore this is nothing but xt minus x. So therefore what is x naught plus h? X naught plus h is nothing but x naught plus h, x naught is xt naught, okay, the x naught. So x naught plus h, what will happen? This is nothing but xt. So that means this is actually xt if you replace h by xt minus xt naught, okay. So this is f of xt minus this is f of x t naught, and this is nothing but xt minus xt naught, and then you take the limit t approaches to t naught. So, this minus this will give you the derivative, okay, d dt of f of x t at t is equal to t naught, and these two combinations, this is goes to 0 because my function f is differentiable at the point x naught, okay, which is x of t naught, because t goes to t naught means x t minus x t naught goes to 0, that means norm of h goes to 0, that means this error term goes to 0, and what this will give, this will be as it is del f gradient of f at x naught, only h vector which is x t minus x t naught, but as t approaches to t naught, you have to somehow take the differentiability, that means divided by t minus t naught, and you will end up with the derivative x prime at t naught. Okay. So, that is the formula, means I have given just a very precise statement, use the differentiability of f at x naught, somehow try to write in this way, and it is given that e of h goes to 0 as h approaches to 0, because my function is differentiable at the point x naught. Then what you do, you replace h by x t minus x t naught, and since t, if t goes to approaches to t naught, then because of the differentiability of capital X at t naught, this difference goes to 0, that means h goes to 0, replace it, use the differentiability of x at t naught, you will end up with this formula. Okay, you complete it. Similarly, as a consequence, I think I have already discussed this chain rule for partial derivatives. If I have a function from R2 to R2, but here it's more general. If I have a map from x from R2 to Rn, so that means if I have u comma v, suppose x1 uv up to xn uv has partial derivatives at the point ab, f is a function from Rn to R, suppose it is differentiable at the point xab. Consider this function, compositions function, f is a map from where to where, f compose x, so that means its f is a map from R2 to range of f is R. So, that means it is a map from R2 to R. So, that means I can talk about the partial derivative of f with respect to two variable u and axis variable, that means del f del u, del f del v, and that is exactly by the earlier one you will have the formula like this is the one. Well, this is a single case, on RL two variable also similar kind of formula will be there, that is a chain rule for partial derivatives. What will happen? So, this is gradient of f at y dot product with the partial derivative of x with respect to u variable at ab. Similarly, del f del partial derivative of capital F with respect to v variable at ab, which is nothing but gradient of f at y dot product with partial derivative of x with respect to v variable at ab, and you just take the dot product, this will have the expressions. So, this is called chain rule for partial derivatives. Okay. So, earlier we will have one like R to Rn or Rn to R. So, composition functions what? It will be a map from where to where, f comes R to R, and this time I have a composition function, it will be a map from R2 to R. So, therefore, you will have two derivatives you have to talk about, partial derivative with respect to u with respect to v, but same set of theorems or same sort of formula will be true, and that is nothing but the chain rule. So, chain rule is the chain rule, I think it is okay for you, because like if I have a functions x and f, suppose x is a map from R to Rn, f is a map from Rn to R, then composition is a map from R to R, then if the given function x and f are differentiable, then the corresponding composition function is differentiable, and you can write the derivative in terms of the derivative of f and the derivative of x. Similarly, this is little more general, because this time I will have a functions from R2 to Rn, not R to Rn. Okay. And if f is a function from Rn to R, then I can suppose the composition makes sense, suppose f composed x makes sense, that means let it be capital F. It will also be a functions from R2 to R. Okay. So, since it is a functions from R2 to R, then I can talk about the partial derivatives, and of course, partial derivatives you can write in terms of the derivative of f, partial derivative of f and partial derivative of x, because x is a map from R2 to Rn. So, you will have n many components. You can talk about the partial derivative of component functions x1 x2, okay, x1 x2 xn, or with respect to the variable u and v, and since f is a function from Rn to Rn, then I can talk about partial derivative of f with respect to x1 x2 xn. So, in terms of the partial derivative of f and in terms of the derivative of capital X, you can have the expression of the partial derivative of capital F, which is nothing but the composition functions. So, that is all about the chain rule, existence of total derivative, partial derivative, directional derivative. Now, as a very nice application, in my next lecture I will talk about what is called this tangent plane and normal. That is the only part is remaining for this section. So, like since I have the kind of notions of total derivative along with partial derivative and directional derivative, then I can have the kind of, as an application I should say, like you'll have a tangent line and normal to a kind of level surface. I will say what do I mean by level surface. So, once I have the notions of gradient, then you will see I will define the level surface, then there will be a corresponding tangent plane and there is a corresponding normal line. So, once we have the notions of differentiability for functions from Rn to Rm, then as an application these are the things will be there, and that will be just if you know the functions from Rn to Rn, if you know the component functions, if your function set is differentiable, then you will have a concept of what is called, you have a notions of what is called level surfaces and or level curve, it depends on which dimension I am talking about, and then you have the concept of tangent plane and normal line. I think this is very few applications are left, maybe I think next lecture I should discuss about that. So, I think I should stop here. Thank you.